Okay, so let's talk about H-R diagrams. These things are reliably show up on every IB exam that has to do with astrophysics because they're just sort of the bread and butter of stars and everything, right? So historically, in 1910, these two guys basically discovered this relationship. So Enyar Hertzsprung, right? So if you're thinking of a name for your kid later on in life, Enyar, don't rule out Enyar, okay? And Henry Norris Russell, and that's where the H and the R comes from, right? At Princeton, they plotted the magnitude versus temperature in independent research. Now, I have no idea how these guys originally plotted it, but if you make a graph like this, I'm going to hand it back to you and say, no, 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 graph it over again. Notice how they've graphed it. This is hot over here, but this is cold over there. So as you go to the right, the temperature actually gets lower, okay? This scale looks like it's upside down. I mean, God help these poor astronomers, right? This scale looks like it's upside down. I mean, why would you do this? Why would anyone do this, right? We got negative numbers on the top and positive numbers on the bottom, but you remember, though, that negative numbers here actually mean that this is bright. So the one axis that they did get right looks like it's wrong, right? And this one, this is dim, okay? Okay, so the thing that's interesting about this, right, is that most of the stars actually fall on something called a main sequence, right? So when stars come together, they burn, and it turns out that the hotter stars are brighter. Now, this is not, a great big surprise, right? Remember, this is a logarithmic scale, so it'd probably be some crazy, asymptote or something like that, right? This is not surprising that hot stars burn brighter. These are also larger stars, okay? They're hot because they're large, and these are smaller stars as well, right? And these are cooler stars on the center, and they're not as bright, okay? And then you get these anomalous things over here. Here you've got a star that's not very hot, but it's bright. Well, remember that the other thing in a star's brightness, right, is basically your brightness is Boltzmann constant times the area of the star times the temperature to the fourth over the distance from us. Well, absolute magnitude gets rid of distance, right? And so if it's not the temperature, it could be the size of the star, right? So these aren't bright because they're hot, they're bright because they're big, right? Here are stars over here that are cold. I'm sorry, they're not cold, they're dim, but they're super hot. These things are super, super hot, but why are they so cold? Well, they must be small. These guys, in fact, are dwarfs. In fact, if you're calling them dwarves, it means that you've read too much Tolkien, because that's not actually a word, it's dwarfs. Okay? That's kind of funny. I thought it was dwarves too. I corrected people, right? Okay. So anyway, these guys are bright but cold because they're big. These guys are giant, and of course these stars are small. There's always a clue there, right? If you take a big look at this, right, I also put some color on here, right? So these stars, the hot stars, are also blue, and these guys are redder stars because they're cooler because of the Wien displacement law. You've learned so much, right? And then these guys are super bright. These guys are dim like that. Okay, and then there's some variation. It's not just a straight line. There's this thing, right? Okay, here is a more sort of a more Gene Coley boils it down because he doesn't want to talk about the spectral type, so he just boils this down to temperature, which works. Here they're talking about spectral type, right? So there's O's and B's and A's. This is historically how they've done it, right? And there's a way to remember all these. Not that you have to, but it's just a funny thing, right? Okay. Here's where the sun is. That's kind of cool. I got this from my astronomy book. Here's white dwarfs and supergiants and red giants, and we'll talk about those later. Okay, but here's how you remember these spectral lines, right? Oh, be a fine girl, kiss me. I don't know, you'll never forget it. It'll be scarred into your memory. Okay, so those spectrum, this is the idea behind these spectra, is that here's the star, here's the thing that's actually radiating it, and what you need to know is that stars have atmospheres. So when you see the light of a star, it's shining through that atmosphere and coming to us. When we observe it, it goes through the atmosphere. We can tell what's in the atmosphere because there's elements in the atmosphere that have these spectral lines, right? And these are like little fingerprints. That's one element, that's a different element. Only when we see them in the sun, we see them as the elements absorb them, because of course this is sending energy through the atmosphere. The atmosphere absorbs particular lines like that one and that one. And if you were a spectroscopist, you could look at that and go, oh, that's, that's hydrogen or helium or something like that, right? So we can tell what's in the atmosphere, and by what's in the atmosphere and how it's ionized and everything, we can tell how hot the star is, right? Here's some spectral lines, and I guess if you're a spectroscopist, you'd know what all these spectral lines are. And notice that they're different. That's all you need to know, and that they are spectral lines, and they're created by the black body radiation from the star being absorbed, particular lines absorbed by the atmosphere. Here's like all the stuff, right? So for an O-type star, it's super, super hot. I mean, just look how hot those things are, right? M-type stars are down there, right? Our star is a G, if you're wondering. You don't need to write all this down. I just wanted you to see that there is some reference. There are some stars. We know which ones are these types of stars. We know what temperatures they are. Notice that there's suffixes, and of course you have to do those backwards too. So 0 is actually the hottest one, and 9 would be the coolest, of course, because Lord knows we couldn't do anything in a normal way. All right, so hot stars are big, bright, brief, and blue. And cool stars, I made this up. This is like no other physics kids anywhere in the country gets this, right? Cool stars are diminutive, that means small, okay? Dim, durable, and you would think there'd be a freaking word in the English language that starts with D that means red. So they're durable and red, right? And we'll talk about why these guys burn up quickly. The big stars, this is weird, right? Burn up quickly, and the small stars burn up slowly. Talk about that next time. Okay, so one of the things you can do with a star, with a H-R diagram, right, is you can actually, if you can read the spectrum, you can go to the H-R diagram and you can guess within a range what its absolute magnitude is. You can get its big M, right? Little m you can just measure, right? You can just measure little m by just pointing a little photometer at it, right? And then of course you can use the distance brightness relationship, right? Which is m minus big M is 5 log d over 10, right? Yeah. Okay, so with this one, this is how bright it appears. That's how bright it really is. We can figure out the distance to it. Okay, let's do an example of that. Okay, I thought it'd be fun to have a BO, right? Okay, so if it's a BO, you go up here. You should go to like the middle of the main sequence, right? And then what do I think? That's probably a negative 4.3 is what I think it is. Okay, so I think our big M is 4.3. I think our little m, well, it tells me that it's 8, right? Okay, so we want to figure out our distance to it. And so what's our formula? Little m minus big M equals 5 log d over 10. All right, so 10 raised to the m minus big M over 5 equals d 10. So let's multiply both sides by 10. D equals, what does it equal? 10 to the m minus big M over 5. I'm too lazy, I'm going to go plus 1. I multiplied that by 10. Huh? Pretty fancy, huh? Let's just try this, right? So that equals, let's see, our little m is 8. 10 raised to the 8 minus 4.3 divided by 5 plus 1. Ha, look at me, huh? That better work or you guys are going to be like laughing at me. Let's see. 10 raised to the, How do you do that on your calculator? Parenthesis. 8 minus 4.3 divided by 5 plus 1. Good God. What if it goes wrong? Okay, yeah, this failed spectacularly. What did I do wrong? D. What did I do? I did something. Oh, okay. Notice that these are negative, right? So that's a -4, huh? That's a teachable moment. We'll leave it in the video. It's -4.3. All right, so minus a -4. There we go. Okay, so I'm going to go second entry. I just have to insert a negative sign. What's a negative sign? Whoops. Okay, so negative. All right, minus a negative. That better work. Ah, that's so good. All right, so now we got the right answer. It was very close, by the way, otherwise. 2884.03, and that's parsecs, right? And of course, we have probably only 1 or 2 sig figs, right? So we have to round it to about there, but I didn't do that. All right, yeah, so just be careful. Kids do that, by the way, on the test, is they forget the minus sign when I ask this question. So don't you do that. All right. I'm going to do another example. You don't have to do it, but hey, I'm going to do it. I'm good for it. Okay, so let's see. A K0 with a little m of 14. So, okay, what is that? That is plus 5. What do you think? That's about 5.8. Think so? Plus 5.8. So little m, or big M, is plus 5.8, right? And then the little m is 14, right? And of course we're going to do the same thing, right? We're going to start off with big M minus, right, equals 5 log of d over 10, right? Okay, we're going to end up with d equaling 10 raised to the minus big M over 5 plus 1. Is that right? I think that's what it was, wasn't it? All right, now let's just go for it, man. Okay, we've already messed up once. We can't mess up anymore. Okay, so let's go 10 raised to the 14 minus 5.8 over 5 plus 1. All right. 10 raised to the 14 minus 5.8 plus 1. Oh wait, did I say divided by 5? I haven't yet. Divided by 5 plus 1. Right parenthesis. 436.515. Now we probably only have a couple sig figs, so we have to say about 440, right, parsecs. All right. Well, I'm tired. That's all there is, baby.